Well, we are here to discuss about one of the most extremely important topics in the field of thermodynamics, which is molar heat capacity. Well, what is molar heat capacity? Molar heat capacity is defined as the amount of heat required by 1 mole of ideal gas to raise its temperature by 1 Kelvin. Well, mathematically, we can say that molar heat capacity, as denoted by the letter C, is equal to, where dq is the amount of heat supplied to the system, dt is the change of temperature, and n is basically what? The number of moles of ideal gas. So here we have the equation for molar heat capacity. Alright, moving on. Well, relating to the term of molar heat capacity, we have two types of molar heat capacities, which is molar heat capacity at constant pressure and molar heat capacity at constant volume. And, well, through mathematical derivations, we have come to know that Cp is equal to Cv plus R, or basically Cp minus Cv is R, where of course from the concept of ideal gases, we know that R is basically what? The ideal gas constant. Now, we will move into the derivation of Cp minus Cv is basically R. Well, how do we prove that Cp minus Cv is basically R? Well, we know that Cp is basically dq over n times dt. Well, we consider for this case that we are dealing with 1 mole of gas, so we did not write the n over here. And again, Cv is basically the same, dq over dt. And we know from the concept of the first law of thermodynamics that where basically dq is the amount of heat supplied, du is basically the change of internal energy of the system, and du is the work done by the system. Now, if we are clear with this, we can say for Cp, it is du plus dw over dt, Cp. And for Cv, it is the same, du plus dw over dt. But wait, we know that in an isochoric process, where the volume is constant, that dw is basically 0. So for Cv, we can write du over dt is basically Cv, since the volume is constant, and in an isochoric process, volume is constant as well. So we label this equation as 1, and for Cv, it is equation number 2. Alright, if we are clear with this concept, then we can write equation 1 as Cp dt is equal to what? Du plus dw, and 2 as what? Cv dt is equal to du. And if we input this equation into this equation, which is 2 inside 1, we get that Cp dt is equal to Cv dt from equation 2 plus dw. And then again we in our previous lectures have learned that the work done dw is pdv, where p is the pressure of the system, which is constant, and dv is the change in volume. So we can say that Cp dt is equal to Cv dt plus pdv from over here. Alright, now let us have this as our third equation. From the concept of ideal gases, we know that PV is equal to nRT, Well, since we are dealing with 1 mole of ideal gas, we can erase this n out. And if we differentiate this with respect to dt, we get that p dt of V is equal to R times d dt of T. And since pressure is constant, we pull that pressure P out of this thing, and we have that p dV over dt is R is equal to p dV is equal to R dt. We multiplied both sides with dt. And if we put this thing into here for the third equation, we have Cp dt is equal to Cv dt plus R dt. Well, why did we do so? Because we had to substitute P dV in terms of dt. And since the dt's cancel themselves off from both sides, if we divide both sides by dt, we get that Cp is equal to Cv plus R. Over here, we canceled the dt's out. And if we subtract both sides by Cv, we get that Cp minus Cv is equal to R. And this is our final relationship between Cp and Cv. Well, that's all.